Hello dear listeners, I am joining from Turkey. I am a PhD student in software engineering at Fırat University. In this presentation, I will present our paper titled Discovery of New Chaotic Systems based on Existing Systems. Chaotic systems are mathematically defined deterministic nonlinear systems. Despite their deterministic structure, they exhibit unpredictable behavior. Unpredictable behavior poses difficulties in terms of synchronization and control. However, they can provide higher security in areas such as communication and encryption. Understanding and controlling chaotic systems is of great importance in many disciplines. Therefore, building chaotic models or obtaining new chaotic systems in science and engineering can lead to new areas of research. Chaotic maps can be divided into two main categories, one-dimensional and multidimensional. Multidimensional maps have more complex dynamic behavior and a larger K area compared to one-dimensional maps. However, multidimensional maps are more difficult and costly to implement due to their complex structure and multiple parameters. In contrast, one-dimensional chaotic maps have the advantage of simple structure, easy implementation, and low computational cost. However, one-dimensional maps have weaknesses such as limited domain of chaotic behavior, non-uniform output sequence, and predictable trajectories. These problems limit the application areas of one-dimensional chaotic maps. Therefore, it's important to improve existing maps or propose new one-dimensional chaotic maps with better chaotic behavior. The literature review showed that many newly proposed systems are essentially a combination of existing systems. This observation inspired that the use of a similar methodology to create new one-dimensional discrete time chaotic maps based on existing one-dimensional chaotic maps. The methodology of the study involves building new maps based on existing one-dimensional chaotic maps and analyzing their dynamic properties. In this context, the new maps were generated and analyzed with the determinate chaos analysis methods. In the study, new one-dimensional discrete time chaotic maps are created by using the mathematical expressions of existing one-dimensional chaotic maps. By using these components, it is aimed to create new maps with strong chaotic behavior. In the method used, existing one-dimensional chaotic map components are randomly combined with different arithmetic operators. Logistic, Bernoulli, and Sinus one-dimensional maps are used in the experiments. The equation of these maps are given in table. Lyapunov exponent and bifurcation diagrams are used to analyze the dynamical properties of the equations generated in this study. Lyapunov exponents are a quantitative chaos analysis method used to evaluate the properties of chaotic systems. This method determines the degree of chaotic behavior by measuring the average exponential deviation of two trajectories that are initially very close to each other. If the Lyapunov exponents of a system is positive, the solution around a given point in the system diverges, that is, chaotic behavior can be observed. When the Lyapunov exponent is 0, this usually means marginal stability. That is, the solution at the given point in the system remains constant or converges to a fixed trajectory. If the Lyapunov exponent is negative, this means that the solution around a given point in the system converges, meaning that the system can often have a periodic trajectory. Bifurcation diagrams are the tool used to visualize the behavior of chaotic systems. This diagram shows the change in the behavior of the system as the value of the control parameter in the system is changed. It can be used to visualize chaotic regions of the system and stable or periodic behavior at a certain parameter values. As an example, the logistic map bifurcation diagram for the range 0, 4 of the control parameter R is given in this figure. For each value of R, the system is first allowed to settle down, and then the successive values of X are plotted for a few hundred iterations. In the experiment, new iterative maps were obtained using random combinations of existing one-dimensional chaotic maps. 4 of the obtained maps are presented in the study. In addition, any of the modes, sines, and cosine functions were randomly applied to the equation expressions. For each control parameter value, the maps was iterated 100 times, and the Lyapunov exponential values were averaged. The initial value of the map state variable was chosen randomly in range 0, 1. In addition, the experiments were analyzed with a control parameter range of 0, 4 and a step interval of 0.01. The generated map, named map1, is given in equation 1. In the equation, R is control parameter. The highest Lyapunov exponent value of the equation was calculated as 2.57 2.5656 at R equals 3.87. When the bifurcation diagram of map1 is analyzed, it is seen that it shows a uniform distribution for all values of R. This coincides with the positive exponent in the Lyapunov exponent graph. The generated map, named map2, is given in equation 2. The highest Lyapunov exponent value of the equation was calculated is 8.62 at R equals 3.08. When the bifurcation diagram is analyzed, it is seen that the generated map doesn't show a uniform distribution. The generated map, named map3, is given in equation 3. The highest Lyapunov exponent value of the equation was calculated as 0.88 at R equals 3.62. When the bifurcation diagram is analyzed, it is seen that the map exhibits chaotic, periodic, and stable states in the range of R 4. The generated map, named map4, is given in equation 4. The highest Lyapunov exponent value of map4 was calculated as 2.05 at R equals 3.94. When the bifurcation diagram is analyzed, it's observed that the map output shows a uniform distribution in regions where the Lyapunov value is positive. It's also observed that map outputs exhibit stable or periodic behavior in some regions. This study aims to develop a new one-dimensional discrete time chaotic maps inspired by existing one-dimensional chaotic maps based on the observations obtained from the literature review. For this purpose, new iterative maps are generated and their Lyapunov exponent and bifurcation diagrams are analyzed. The obtained results confirm that the proposed maps exhibit chaotic behavior. These analyses show that the proposed chaotic equations can exhibit different behaviors under various parameter values, and these equations can have various applications in potential applications. The main contribution of this work is the successful implementation of a methodology for the generation of new chaotic equations based on a combination of existing systems. By deepening the understanding of chaos theory and dynamical systems, the proposed methodology can guide future work in this area. In conclusion, this work highlights the importance of a new approach to the modeling and analysis of chaotic systems and offers a new perspective to research in this field. In the future, an important research direction will be to apply the proposed equations in a wider context and to investigate how this system can be used in practical applications. Furthermore, obtaining more robust chaotic structure using optimization methods represents a different research area in this field. Thank you for your time and engagement. If you have any questions or feedback, please feel free to contact us by email.